Right now, the future of technology depends on one of the strangest machines humanity have ever built. A machine so extreme it fires lasers at droplets of molten tin 50,000 times a second, just to create a flash of invisible light. It is the only reason the most advanced chips on Earth even exist. For years, EUV lithography was the absolute peak of semiconductor engineering, and now it's hitting a hard physics wall. And this new machine they are building to break through that wall is the strangest chip-making tool ever attempted. I'm a chip design engineer, and honestly, I never thought that the future of computing will drift so closely to the particle physics. The chips keep shrinking, but the machines required to build them keep growing. Subscribe to the channel and let me explain. Most people think AI race is about GPUs. It's not. The real bottleneck is light, because modern chips only exist if humanity can reliably print nanoscopic structures onto silicon. And the smaller the transistor becomes, the harder it gets. We are basically etching rocks with invisible light at that point. Lithography is essentially photography for computer chips. You generate an incredibly precise beam of light. That light travels through a maze of mirrors, reflects off a photomask containing the chip design, and eventually reaches the silicon wafer below. The wafer is coated with a special chemical layer called photoresist. And when the photons hit that surface, they chemically change the material in extremely precise locations. At that moment, the design is effectively printed onto the wafer. And then comes the rest of the manufacturing process: etching, deposition, doping, stacking layers again and again, until billions of transistors emerge from an ultra-pure slice of silicon, at least when everything goes right. Because at the foundation of all lithography is just one simple problem: your wavelength. It defines how small your features can be. And eventually, the industry reached a point where the light itself became too large, way larger than the patterns it was trying to print. For years, chip makers relied on deep ultraviolet lithography, 193 nanometer light, but they kept trying to print smaller and smaller features with it anyway. So engineers started to use different tricks. You take one complex pattern and split it into several simpler ones. Print the first part of the pattern, etch it, expose the second half, then etch it again. Suddenly, you can create features smaller than the original light should physically allow. This became known as multi-patterning. Well, we are currently doing multi-patterning in the studio. And this is where chip manufacturing started turning into an engineering maze. The industry was forcing older lithography tools to print features they were never meant to handle. Every extra pattern meant more masks, more alignment steps, more chances for things to go wrong and destroy multi-million-dollar wafers. And the industry kept forcing the old light to print features it was never designed to print. And eventually this workaround became harder than the scaling itself. So ASML and the semiconductor industry did something extraordinary. They jumped to an entirely new type of light: extreme ultraviolet light with 13.5 nanometer wavelength. Small enough to print features only a few nanometers wide, it was one of the biggest technological leaps in history. And the problem was that just a generation of this light pushed humanity to the edge of what was physically possible. Inside the machine, microscopic droplets of molten tin are fired through a vacuum chamber. A first laser pulse hits the droplet and reshapes it for the main blast. Then comes the real hit. A giant CO2 laser slams into the tin droplet with enormous energy, and the tin instantly explodes into plasma. And for a tiny fraction of a second, that explosion emits the rare 13.5 nanometer EUV light needed to print advanced transistors. And that is how modern microchips begin. But the strange thing is of how little of usable light this whole complex process actually produces. After all of this complexity, only a tiny fraction of the original energy ever reaches the wafer. Some estimates place the wall plug efficiency below 0.1%, which is astonishingly inefficient way to generate light. And controlling that light turns out to be even harder. It is so extreme that even air and glass immediately absorbs it, meaning blocks it completely. So the entire machine operates in vacuum. The UV light bounces across a maze of mirrors, reflects off the mask carrying the chip design, and finally reaches the wafer. And that tiny flash of light is now the foundation of modern computing. But the real problem starts at 3 nanometers and below. Shot noise. At these scales, fabs start approaching stochastic limits, meaning there are literally not enough photons hitting the wafer consistently enough to print perfect features. Physics becomes statistical, random. Imagine trying to spray paint a perfect nanoscopic line, but some of the paint particles never arrive. At normal scales, that doesn't matter, but at 3 nanometers, it becomes a problem. And at some point, you start fighting probability itself. And that's how ASML became one of the most important companies in the world. Because generating this light reliably and at scale became one of the defining engineering problems of modern computing. But now, for the first time in many years, the semiconductor industry is seriously considering a different approach. Instead of exploding molten tin with giant lasers, they want to generate EUV using electrons moving close to the speed of light inside particle accelerators. And one of the companies pursuing this approach is the American X-Light. Their idea is to build something called free electron laser, or FEL, which sounds way cheaper than it will actually be because it will cost close to $1 billion. Free electron lasers were never invented for chip manufacturing. They are now mostly used as scientific instruments. They are like world's most powerful slow-motion cameras for atoms, molecules, proteins, and materials. And scientists use them to watch matter change at absurdly small scales and absurdly fast speeds. Basically, FELs were built to study nature. But now the semiconductor industry may need them to manufacture nature's smallest devices. FELs generate light directly from fast-moving electrons. And if it works, it will not just challenge ASML, it could push the semiconductor industry toward a completely different kind of factory. Now, this is where the story takes an unexpected turn, because a free electron laser doesn't work like a normal laser at all. Traditional lasers use atoms. You excite a material, the atoms release photons, and you get a beam of light. While a free electron laser skips the atoms entirely. Instead, it fires a beam of electrons close to the speed of light through a long magnetic structure. The magnets force the electrons to rapidly zigzag as they move forward. And when particles suddenly change direction at these speeds, they emit light. At first, that light is weak, but then something interesting starts to happen inside the beam. The electrons start grouping together into synchronized bunches. And once that happens, the emitted light suddenly becomes dramatically more powerful and focused. By carefully tuning the electron beam and magnetic structure, we can make that beam produce the EUV light. And this is the moment where semiconductor manufacturing starts drifting into particle physics. So why does the industry suddenly paying attention to this? Because traditional EUV systems are becoming harder and harder to scale. They still work, very well actually, but every increase in performance now requires more power, more complexity, and more engineering effort just to keep progress moving forward. And at the same time, AI demand exploding. Data centers are eating up the world and require enormous numbers of advanced chips, which means fabs suddenly need to process far more wafers than ever before. And this is also an economics problem, because the faster you can print wafers, the more chips you can produce from a chip factory that already costs you tens of billions of dollars to build. And this is where FELs technology becomes really interesting, because the single FEL machine can generate way more light than a single EUV machine. And in lithography, more light means faster printing. Potentially enough light that one centralized source could feed multiple lithography scanners simultaneously. And this would dramatically change the architecture of modern chip factories. But there is another reason why this matters. Today's entire EUV ecosystem is built around one specific wavelength, 13.5 nanometers, and that single number underpins much of modern computing. But FELs are tunable. You can change the electron beam and you can change the magnetic structure, and in principle you can push toward even smaller wavelength. Some FEL facilities already operate around 6 nanometer wavelength, and some even below 1 nanometer, entering the X-ray range. And that means that in principle they could eventually print transistor features even smaller than what today EUV systems can realistically achieve with any clever tricks. Which is extraordinary if you think about it. And suddenly it's not only about improving the current EUV systems, but the question is whether there is a path for the semiconductor industry beyond them altogether. And the strange part is, machines like this already exist, with some of the most interesting developments now happening in the United States, Japan, and China. And interestingly, each of them is taking this idea into a completely different direction. And we will have a closer look at it in a moment. But before that, if you're paying separate subscriptions to ChatGPT, Claude, presentation tool, image generator, you're basically bleeding money. That's exactly why I started using Genspark. It's all-in-one AI workspace. And honestly, their growth has been insane. They've reached a $250 million annual run rate in just 12 months. Traditional AI just chats with you. Genspark actually executes the work. For deep semiconductor and AI research, I use their super agent. What's impressive is that it combines all the top AI models like Claude Opus and Gemini together, which gives you much stronger research results and cross-validation than relying on a single model. Then it can even turn research directly into slides. You can use it for AI sheets, presentations, meeting notes, emails, and even building websites. You still decide what matters, while Genspark removes the repetitive busy work. My favorite feature by far is their new feature Speakly, because I manage multiple teams and I need to write lots of emails and messages. Instead of slowly typing it down, I just speak all my thoughts, and it then automatically turns them into a polished email about 4 times faster than typing. I genuinely love this feature. So instead of paying separately for ChatGPT, Claude, Canva, and Gamma, Genspark puts everything in one place. One $20 subscription gives you access to the top AI models plus AI chat, plus unlimited image generation for all paid users in 2026. Check it out through the link below to try it for free with sign-up credits available. Now back to the future of chip factories. So what happens when you actually build one of these things? To find out, we first have to look at the European FEL in Germany. ASML EUV machines are famous for being gigantic, the size of a double-decker bus. So how do we solve the next bottleneck? By considering even larger machines, larger than a football stadium. A gigantic free electron laser stretching more than 3 kilometers underground across Hamburg. And it was never designed to print chips. Scientists use it to study molecules, proteins, chemical reactions, and matter. Basically, it's one of the most advanced light generation systems humanity have ever built. But then semiconductor engineers started paying attention, because unlike most FEL systems, which pulse relatively slowly, this FEL fires up to 27 times per second. And future chip factories may require exactly this kind of industrial-scale photon output, powerful enough to feed manufacturing lines around the clock. And then there is the infrastructure itself. Parts of the machine are cooled close to absolute zero using superconducting systems. The accelerator stretches for kilometers underground. And suddenly, semiconductor industry starts drifting into territory that looks nothing like a modern chip factory. Not rows of manufacturing tools, but giant infrastructure, vacuum tunnels, superconducting systems, particle accelerators underneath the fab itself. And this is where the story gets very interesting. Because if this approach actually works, then the future chip factories may look more like CERN. Today, every ASML EUV scanner generates its own light locally. Each machine operates mostly independently, and even if one scanner fails, the rest of the fab keeps running. But a free electron laser changes this model completely, because instead of each EUV scanner having its own light source, multiple scanners can be connected to a single powerful light generator. And this is where economics start to be very interesting. A sufficiently powerful FEL could generate several kilowatts of EUV light, enough to feed up to 12 scanners at once, one particle accelerator powering an entire chip factory. But that creates a new problem, because if a FEL becomes the heart of the factory, one failure could turn the entire factory dark. And suddenly, the scale of this starts becoming hard to ignore, because shrinking transistors may soon require infrastructure on the scale of national labs. Basically, it turns it into fusion between chip factory, particle physics facility, and a power plant. And then a natural question emerges. How do you actually commercialize something like this? Factories don't work like research experiments. They need stable uptime, 24 hours a day, every single day. And this is where the company X-Light enters the story. Their goal is not to build another giant scientific facility, but to shrink this entire idea into something fabs could realistically deploy. X-Light was founded by accelerator physicists coming out of places like SLAC, which is Stanford Linear Accelerator Center, one of the most advanced accelerator labs in the world. And their idea is straightforward. Take decades of accelerator research, remove as much complexity of science project as possible, and turn it into factory equipment. Instead of redesigning the entire fab, X-Light wants to replace only the EUV light source itself. They plan to keep the scanners, keep the mirrors, keep most of the existing lithography infrastructure, just replace the light generation system entirely. So they get rid of thin plasma and exploding droplets, using only electrons accelerated through a linear machine generating EUV light directly. And their targets are ambitious, around 4 times more EUV power than current systems, with 50% lower operating cost. But when they say compact, don't even dare to imagine something small. This is still a giant linear accelerator sitting next to the fab, routing EUV light into the scanners. But compared to kilometer-scale facilities like FEL we just discussed, these suddenly start looking practical. And this is where the American strategy becomes clear. Shrink accelerator physics enough that semiconductor facilities can actually live with it. But Japan looked at exactly the same problem and came to a completely different conclusion. At Japanese KEK, they believe that size is not the biggest problem. Power is. So they are completely focused on efficiency. That is the core idea behind something called an energy recovery LINAC. Normally, electrons get accelerated once, generate light, and then get dumped away as waste energy. Instead, this system tries to loop those electrons back through the machine. And this is a clever part, because as the electrons slow down, they give a large portion of their remaining energy back into the accelerator itself. And that recovered energy then helps power the next electron beam. It's basically regenerative braking, but for particle accelerators. And suddenly, the economics of the entire system start to look entirely different. Because if you can recycle energy efficiently, you can push much higher beam without exploding the electricity costs. That is why Japan is so interested in this architecture. Researchers at KEK believes that future free electron laser systems could potentially generate around 10 kilowatts of EUV power. And that is an astonishing number if we compare it to the modern EUV systems, which operate in the 100 watt to 500 watt range. And importantly, they will be using it not just for one machine, but potentially it will be enough to power multiple scanners simultaneously. But the catch is, right now, this is still experimental technology, and they are nowhere near commercial lithography yet. And this is where the story takes another turn. America is trying to make accelerator physics compact enough for fabs. Japan is trying to make it efficient enough to make economic sense. China decided to scale it up instead. And meanwhile, ASML is still pushing the existing EUV architecture further than almost anyone thought possible. You see different countries and completely different strategies. And honestly, the most fascinating part of this story is happening right now in China. Because for China, this is not a technological upgrade. This is strategic necessity. Right now, China cannot buy ASML's most advanced EUV systems because of export restrictions. And without advanced lithography, building cutting-edge AI chips becomes extremely difficult. Multi-patterning with DUV can only take you that far. So China started to invest heavily into alternatives, and one of their most important projects is so-called SSMB. Steady-state microbunching led by researchers connected to Tsinghua University. And unlike the American or Japanese approaches, China is not trying to squeeze accelerators neatly into existing fabs. They want to rebuild entire factory around the machine itself. In their concept, they are using a massive circular storage ring, roughly 150 meters around, where electrons continuously circulate at near light speed. Instead of accelerating electrons once through a straight line, China keeps them moving continuously inside the ring. Then another laser organizes those electrons into extremely tight bunches, causing them to emit powerful EUV light continuously. And that matters, because one powerful EUV light source can feed huge amount of EUV scanners simultaneously. So China is focusing on scale. Massive, centralized EUV infrastructure. And at that point, this is looking less like competition over chips and more like countries building entirely different industrial systems for controlling light itself. And once you look at who is investing in this technology, a pattern starts emerging. Like Japan, who wants to secure its semiconductor future through projects like Rapidus. And I actually made a deep dive on this interesting chip factory. Subscribe to the channel now so you can watch it afterwards. The US wants alternatives as AI demand explodes. China wants independence from Western restrictions. And meanwhile, ASML still controls one of the most important choke points in modern technology, because whoever controls the light controls the future of chip making. And this is where the story becomes less romantic, because even ASML themselves considered this new particle accelerator approach years ago, but they still stayed with thin plasma. And that says a lot. Because despite all that insane complexity, today's EUV systems actually work, not experimentally, but inside real fabs, every day. And in semiconductor manufacturing, that matters more than elegant physics. A free electron laser may look cleaner on paper, but fabs have to be optimized for uptime. The semiconductor industry rewards the machine that keeps running at 3 in the morning without freezing a billion-dollar production line. And this is where FELs technology faces its hardest transition. Scientific demonstrations are exciting, but the challenge is making particle accelerators reliable enough for semiconductor fabs. And even if engineers solve all of that, there is still one issue: timing. Because the AI infrastructure build-out is already happening right now. TSMC and Intel are expanding aggressively in Arizona. In Texas, projects like TerraFab are moving at astonishing speeds. And I have made deep dives on both. The industry needs more compute and more advanced manufacturing capacity right now, immediately, not in 10 years from now. Which means ASML will continue dominating because its machines already exist, and the entire semiconductor ecosystem already knows how to build the manufacturing recipe around them. History is full of examples where technologies were technically better, but commercially late. And this is what makes this story so interesting. Because the semiconductor industry may already be building the next generation of factories before it fully knows what the next generation of lithography will look like. Because the next era of chip manufacturing may not be defined only by smaller transistors, but by who can build the most extreme light source. And that creates a strange paradox, because chips and transistors keep shrinking while machines required to build them keep growing larger and larger, which is fairly unexpected direction from the industry, which is obsessed with making things smaller. Because if this approach actually works, printing the smallest transistors on Earth may require building the largest factories in human history. If you enjoyed this episode, make sure to watch this breakdown on the largest and the most controversial chip factory being built right now in Texas. Love you guys, and I will see you there.